Welcome back to the A Level Physics podcast, and today we will be embarking on an adventure through telescopes. So in this episode we will dive deep into the A Level Astrophysics telescope section, focusing on the marvels that lead us to touch the stars from our backyard. So grab your star maps and let's get started. So first up, let's talk about astronomical telescopes, comprised of two converging lenses. So essentially picture a ray diagram with light converging to form an image. So this setup is how we achieve angular magnification, essentially zooming in on an object or the universe. Remember, however, magnification is the ratio of the focal lengths of the objective to the eyepiece lens. Why does this matter? Well, because it allows us to see the details of celestial objects far beyond the reach of the naked eye. So essentially how this is working is we've got two lenses set apart. We have our objective lens and our eyepiece lens. We first have the rays coming in parallel to the objective lens. By the way, both of these lenses are both convex. And then our objective lens will focus these parallel rays towards each other, and they will cross at a focal point, and that focal point will be along something called a focal plane. And then once the distance between that objective lens and the focal point is FO, which is the objective lens between the objective lens and the focal plane. It's the difference between there, and then our rays are going to go past this focal point and they're going to head towards the eyepiece lens, and the distance between the plane and the eyepiece lens is FE. And FO over FE is magnification. This is why if we increase our objective lens distance, we will increase our magnification. So, how might changing focal lengths of distances of the lens affect what we see? Well, we've just answered that question. So moving on, let's reflect on reflecting telescopes, especially the Cassegrain arrangement. So essentially imagine a parabolic concave mirror collecting light and then bouncing it off of a convex secondary mirror through a hole in the primary and then going to an eyepiece. So this design minimizes aberrations because of this parabolic concave mirror. So these aberrations are those pesky distortions, like the spherical and chromatic ones, that can blur our cosmic views. So reflectors versus refractors. So it's a tale of clarity and precision. So reflecting telescopes with the mirrors avoid chromatic aberration and allow for larger apertures. Ever wondered why professional observatories prefer reflectors? That is why. So, consider how aberrations might affect your view of the stars. Why is minimizing them crucial? So, beyond visible light, we will now look at radio and X-ray telescopes. So, let's expand our horizons beyond the visible light. We have radio telescopes, we have infrared, ultraviolet, X-ray telescopes open to the windows of the universe that will go to our eyes. Or optical telescopes can't see. So they're beyond our vision, essentially.
Joshua Barnes is calling.
So these types of telescopes differ in structure and use, but each has a unique way of collecting and resolving the cosmos' mysteries. So from giant dishes of radio telescopes to orbital observatories capturing high-energy X-rays, these instruments reveal the universe's hidden layers. But how do they compare in terms of resolving power, and what can they detect? So a question for you: why might astronomers use different types of telescopes to study the same celestial object? We are now covering segment 4, which is the power of diameter. So, our cosmic journey wouldn't be complete without discussing the power of diameter. It's all about aperture. The larger, the better. Why? Why? Because of the Rayleigh criterion, which tells us about the minimum angular resolution a telescope can achieve. And remember, collecting power scales with the diameter squared. It's not just size for the sake of size. It's about delving deeper into the universe, resolving finer details and capturing more light. And in the world of detectors, the CCD, which is a charge-coupled device, revolutionises what we can capture with superior quantum efficiency and resolution compared to the human eye. So a question for you. Imagine what we could discover with even larger telescopes. How does aperture, size, influence our understanding of the universe? Next up is our conclusion. I just want to also add that we have two different types of lenses, the first being convex. So when we have incident parallel rays hitting a convex lens, they will essentially spread out, whereas a concave lens, they will move towards each other. Coming to a focus point. So, to conclude, telescopes are more than just tools. They are portals to the universe, enabling us to see beyond the visible, understand celestial mechanics, and unravel the cosmos' mysteries. So today we've journeyed through the key concepts of AQA Astrophysics A Level module. But remember, each telescope, whether in your backyard or orbiting Earth, is a testament to human curiosity and our quest for knowledge. So keep gazing upwards, and who knows what mysteries you'll uncover. Thanks for tuning into this podcast. Stay curious. Until next time.